talks on dynamical core to operational models. I'm chairing the session. My name is Takeshi Enomoto from Kyoto University. The first speaker is Samad Kadori of Environment Canada. The title is the CMC 15-kilometer operational deterministic global forecast system with Yin-Yang.
Thank you. I want to thank the organizer to give me the chance to give this talk. This work was done with collaboration of Vivian Lee, my colleague.
You can't hear here.
It's microphone off.
Microphone is not working. So I will present this work. This work was done with collaboration of Vivian Lee, my colleague. I will talk about the future operational global model in CMC. So I will give brief motivation. I will present a model problem with solution methods. So I will present also some numerical results. I will give some word about data assimilation work. So for this work, I will compare two systems, global and Yin-Yang, with those resolutions, 15 kilometers at 49 degree north, latitude 49, and 15 kilometers at the equator for Yin-Yang. So one problem associated with the construction of a global atmospheric model is the numerical representation of spherical geometry. So the current operational model uses lat-long, which we know has pole problem. So you have pole singularity and convergence of meridians near the pole. So we want to switch to Yin-Yang. So Yin-Yang was introduced by Kajiyama and Sato in 2004. It's basically a composite grid, an overlapping grid, no matching grid. So it's composite, it's pole-free and is composed of two pieces of lat-long. So we still have lat-long. Donc, all those nice properties of lat-long, orthogonality, easy representation of operator, and also most important that all those numerical schemes developed for lat-long can be adapted easily to lat-long, to Yin-Yang grid. And also, domain decomposition method or Schwarz method is easily implemented to this kind of grid. You can do it by two-way coupling of two limited area, of the two-way nesting if you want. Here model problem. We have no hydrostatic model, but here I will present only hydrostatic. The main difference is that you have two extra variables, vertical velocity and departure from log pressure, log hydrostatic pressure. So here we have momentum equation, thermodynamic equation, continuity equation, and diagnostic hydrostatic equation. So V is wind component, F Coriolis, T temperature, B is metric term, S is proportional to log surface pressure. Here we have at the right hand side, big F are the physical forcing, some operator, material derivative, horizontal divergence, wind images, horizontal gradient. So we use log pressure vertical zeta is hybrid. We use this small r to be able to flatten when we want and where we want this here you see two comparison below 2 hectopascal. We have the more level, but we have present only those below 2 hectopascal. So with variable r, we can flatten below 2 hectopascal, and no problem with those tests that pass through a maintain. So the solution is based on Schwarz methods. It's basically domain decomposition. So we have two domains, yin and yang, and we solve in each domain hydrostatic primitive equation iteratively in each subdomain, and we have no overlapping grid. So we exchange variable by interpolation at the interfaces. We use cubic Lagrange interpolation, and in each subdomain we use the same local solver with same time step, which is two time levels in the Lagrangian method with implicit discretization. This is implicit. So we have to solve an elliptic problem 4 times, as presented in previous presentation. We have also finite difference and horizontal Arakawa-C and finite difference and vertical Charny-Phillips, 2 staggered grid. Spatial discretization. So here we replace all vertical finite difference by this operator delta zeta and averaging operator when we need it. Here we present Charny-Phillips with placement of variable. We use Arakawa-C. This is all known. So temporal discretization we use as Cote and Staniforth in 1908, and also Ye and Orr. So each prognostic equation can be written like this. So we do time discretization and YTNG term long trajectory. This trajectory is an approximation of these systems when for vertical displacement, we suppose acceleration 0 as usual in semi-Lagrangian, but for horizontal, so we try to keep the motion on the spherical surfaces. Small r is the position on the sphere. Boundary condition, so we have material surfaces, surface and top, and we do zeta dot equals 0 at surface at top, and we have horizontal. In horizontal, we have directly type boundary condition. So I said that we have to solve 3D elliptic boundary value problem and Yin-Yang. So this is elliptic problem. So we can write it as an operator A acting in big P, equal right hand side. P is combination of J potential and S, which is log surface pressure. So we have the following bottom and top boundary condition. Right hand side. So we solve this by iterative Schwarz method. So we have in Yin-Yang the elliptic problem and Yang elliptic problem with the interface operator. And we solve this iteratively. We have this iterator K. We solve this iteratively until convergence. And once we have this big P, we have all the variables by back substitution. It's very easy. So for both systems, we use an adiabatic digital filter with 6 hours span at the beginning of the run. And we also have a scale selective del 6 applied to variable UV, W, and zeta dot. Here we have all physical parameterization used in GDPS. So we have boundary layer turbulence, orography blocking, orography gravity wave, radiation, etc. So the global forecast is done as 2 coupling between 2 lambs. So for people who do limited area modeling, it's very easy to implement this. So we have 2 lambs and we extend each one by a static alloy. And nesting zone play the same role as piloting region in modeling limited area. So we exchange this by cubic Lagrange between both. Here we have communication pattern. Here you can see that we have yin and yang, and we divide between 16 processors, 1, 2, 3, 4 by 4, yin and yang, just as example to give a communication pattern, and you see how it is. For geophysical field, we calculate independently in the yin and yang those fields. I give some example here: filtered topography, land fraction, vegetation, etc. Here I represent in yin and yang this field, filtered topography. This is the grid that will be used operationally. So it's mainly a rotated yin-yang. So here we saw yin, and we want to put North America inside yin. This is politics, but no. For numerical result, I will present two series of tests for 42 winter cases and 42 summer cases, integrated by initial analysis in 2008, and each case is 5 days forecast compared to observation. I will use two configuration, yin-yang. This is 15 kilometers at equator, that long. This is only 50 kilometers at the Canada. Now, people who work with that long want me to compare with yin-yang 15 kilometers, because they said if they go with that long, they will go with it. So here we have some results. Objective evaluation for 44 summer cases, 5 days. Here we have wind component, UV, geopotential, temperature, TT, and dew point pressure, ES. So as we see, same result. North America winter. I forgot to say that the red is yin-yang and the blue is lifelong. We have both, and we have RMS for people that don't know this. RMS is this, and bias is this. Okay. So red one is yin-yang. Here Europe, summer cases, no problem, same results. Winter, Europe, no problem. World objective evaluation, summer. We have even a small better evaluation for yin-yang, and world evaluation for winter. World objective evaluation. So we are happy with those results. Here I represent precipitation and yin-yang. I will escape this one. I have another one without lens. Same. So we have 24 hours precipitation forecast without geographical eye. So here we have yin-yang precipitation field superposed and the global yin-yang. So here we have yin and red, yang and blue, and here you can see overlap. So we check those number, it's almost same. So here we have Yin-Yang precipitation, field superposed and precipitation from globe light lamp. It's a little bit confusing. So we have yin and red, yang and blue, and black is for light lamp. And we were happy. Hurricane Faye was in this analysis that's happened in 2008. Here we can see 24-hour precipitation forecast, accumulated precipitation field from Yin-Yang, and accumulated precipitation from J-Black. Same. We were happy to see that. So we have some difference, that's sure, because we have not same resolution, not same point, not same grid point, but same pattern, almost same numbers. Here some timing in IBM P7. Here I will show only 26% of operational run. Here I include all the operational, is as operational. So we have Team Light Long with this resolution. This is total number of grid points. Jamie Yin-Yang, this resolution, total number of grid points. Processor topology, along longitude in px, along latitude in py. Vertical is not decomposed as usual, and OpenMP. We have 44 nodes. Here only 38 nodes. And we can state that we have almost the same times, the same total net times. Divided between dynamic, then step, and physics. A big part of dynamic are advection, elliptic solver, back substitution. When you got solution from elliptic, you do back substitution to calculate other variable. This is named here back substitution. We have also, after doing dynamic and physics, we applied del 6. They applied it implicit, we don't have choice, that long grid. I will happy to see an explicit one on that long. And we do an explicit and Yin-Yang. We do sponges implicitly and explicitly. We can do it because we don't have this problem, pole problem. This is output for dynamics, output for physics. This is nest PC. This is how you cast you as communication and everything when we do nesting, double nesting between yin and yang. So we saw that the big is advection for flat long, big time, and this is people try to don't do too much processor along longitude because this will introduce a global communication in transpose. Because we use 4E and as solver, elliptic solver. And we see here that solver is big times here, the bigger one, but it's not that much. Here we try to go to 75 nodes, but only by doubling OpenMP. This case we use A50 as you see, and we cannot go farther than 20 in longitude because we have only 80 vertical. So vertical divided by 20 give you only 4. So we can, if you want to go, we have to go by OpenMP later. So doubling this, we double for physics. Physics is completely pointwise. So we double OpenMP, you divide by 2 the time, but you cannot divide by 2 the dynamic because it's hybrid, and some places we have OpenMP, so you can get some benefits from that, but it's not double. Here we do the same, but using iterative solver. We have also this. This iterative solver is flux GMRS, flexible GMRS. It's good with block Jacobi perconditioner. So this one, a 50 is very hard to base. I know what I said, but it's scalable. Iterative can be scalable and everything. I will say some word about work of data assimilation group. This slide is given to me by Mark Brunner. So basically NVAR approach is currently being tested to replace 4D VAR. It's a hybrid approach using NKF and variational assimilation by making the use of 4D ensemble. NVAR perform 4D analysis without the need. This is very important. Tangent, linear, and adjoint forecast model. And we get some 10 to 20% of the computational resources. We have some preliminary result for latitude, longitude grid, but not yet for Yin-Yang. This is what we have now. So GMLAT long 25. Every 6 hours we do this. Background check, bias correction, 4D variational assimilation. We run the model and we go back. We have 2 independent systems, global deterministic and global ensemble prediction system. Here the future, a new NVAR system, 2-way dependence. We have dependence between, you see, that NKF gave something to NVAR. So we don't need to do tangent linear and adjoint. And we will use Yin-Yang 15 kilometers. And this one must be 50 kilometers. I forgot, I'm sorry. Thank you.
Time for discussion. I have a question. In Latin version of GEM, there is a version you can concentrate grid.
Variable.
Do you have?
Yeah, we keep all those things nesting by verticals, everything. We keep this. We have this already. So we keep this also for limited area also.
I just want to know what do you do with the physics in the overlap points? Do you calculate, you interpolate your field and you pass them to the physics, or you interpolate the physics?
Physics is done inside each panel. So we do dynamics, we do physics, and after this we interpolate and this static halo from the other. That's I can show you how it is done.
Okay.
You are using two grids.
Yeah.
How do you keep track of the coordinate variables? Do you have to use any data structures in your program, or you do it?
I didn't hear you. Say that.
Basically, you are using two sheets of the sphere.
Two panels.
Yeah, yin and yang. How do you keep track of these variables, the coordinate variables in integration?
Corners.
You have in which variable and which sheet, especially when it involves in integrations and exchange of variables.
We exchange at solver. We exchange that solver
Yeah.
until convergence. We exchange also as in nonlinear solve. So when we do back substitution, we have UV velocities, and we need this. So we exchange to do another advection trajectory calculation and everything. So we do this, and we exchange at the end of time step. We do like limited area at the end of time step.
Okay,
So,
let's.
tensors.
Oh, sorry. Sorry, time is up. Let's thank Ade-sama again.